Hello, how's it going? In the previous video, we basically got a map up and running. And I mentioned that we were doing it in the most naive way possible. And now we're going to speed it up. So to start with, what I've done is in the render system, I've gone ahead and given this system a variable which tracks the number of draw calls. So anytime we go down here, anytime GL end is called and a polygon has been issued, that counts as one draw call. At the start of every update, we initialize that to 0. We go ahead, we do all of our rendering, then we return how many draw calls were issued. And this is the situation. Okay, so as you can see, there are 600 draw calls being issued, and we've got a frame time of about 17 to 18 milliseconds, which is a little worse than 60 frames per second. In other words, for what we're doing, it's really bad. And like I've been saying, there are many reasons for this. One reason is that for every wall object, we are actually drawing each of the 4 walls around that cube, regardless of how visible they are. And then another situation is that we're basically drawing everything in the world. And, despite the fact that we can just see this stuff here. And then another issue is that we are taking this array and in Python looping through everything and attempting to draw, despite the fact that some of those blocks are empty and we should know ahead of time that they're empty. So this leads us to the optimizations that I'm going to investigate. Here I've just taken a baseline, and these are all the optimizations I'm going to do. These two I'm going to do today. So today I'm going to do what I call static optimizations, and those are optimizations that we can apply without needing to, we can basically do them once. We can do them once at the setup, and then we don't need to do anything else. And then these other optimizations will be calculated on a per frame basis. And the cool thing about these optimizations is they are pretty much all modular, apart from maybe the last two, but I'll get to that when we get to it. Long story short, by the time the method I've got in mind for occlusion culling should also do view culling, so that'll be fine. But basically, we can slot these optimizations on one at a time. But that's enough stalling. For now, culled planes. So the idea with culled planes is, let's say, this is really bad, but let's say we've got a wall block, and that wall block has 4 sides. And each of those sides can be indicated with a bit mask. So we have, I forget what the exact notation is. I sort of hard-coded this, but let's say east, west, north, and south. Each of these are a unique pattern of power of 2. And so in a binary number, they can be represented in unique bit positions within that number. So let's say if we've got a block and it's hanging around in empty space, so none of these sides are blocked by other sides, then it's got full visibility. That's a mask value of 15. Let's say, for instance, that there is a block below it, which is masking out the side corresponding to a value of 4. All we would do is mask out that value of 4, make it 0 in that bit position, and then this is a mask value of 11, and then when we go to draw that mask, we can inspect that integer and say, well, that bit hasn't been set, so don't draw that wall. That's the basic idea. So I'm going to have to spiral into this from a few different angles, but to start with, I'll just go right down to the guts of it. I'll go to my render system, and I'll go down to the section where we can leave this because the ceiling and floor, they're totally going to be fine. But yeah, this wall stuff. So In addition to all this info, I'm also going to need to take in a mask. And then before I do any of this stuff, I'll do my mask check. Okay, so what this is doing is if I take 1 and shift it up to the given bit position, then this will be going through the powers of 2. So this will be going 1, 2, 4, 8, just like that. What I'll be doing here is taking a bitwise AND between those numbers, and this will basically be indicating whether the given bit within that mask has been set. If it has not been set, then this bitwise AND will give me a value of 0, in which case I can skip ahead to the next phase. So then what I'll need to do is in my component registry, I'll need to track some sort of mask. So I'll go to my component registry up above. I'll just say, and then at the point where I create the walls, I'll also go ahead and create the wall mask. So then in my render system, when I capture all the info that I need, I'll also capture the wall mask. Cool. And then in my render loop, there's just a lot of button, what was it? License plate. That's it. A lot of license plate stamping at the moment. But when we go to draw the wall, we also, the appropriate mask position. I should say the mask at the position. You know what I'm saying. Okay, cool. So if I run this right now, it will do nothing because the mask is, well, as in no walls will show up because the mask will be initialized to 0. So what I'll need to do is in the world system, at the point at which we load in this data, I want to also set the mask. So what I'll do is write down just under, maybe before update, but under load array, I'll make another function, which I call mask out. And this will take in the data, which will basically be the wall data. And it will also take in a mask, which it should populate. And just the same as load array, it will actually return that mask that it just populated. So there's a few stages to this. The first stage is we'll look through everything and we'll just, wherever there's a wall, we'll give it a full mask to start with. Cool. So like I said, we just look through everywhere we see a wall, we initialize that, like fully like draw everything. Cool. So just to test that, I'll go ahead and right after I make my walls, okay, so excellent. As you can see, we have pretty much got the same performance. Maybe a little bit worse because we're doing that extra check, which is not saving us any time at the moment. But let's start to get this working in our favor. So first thing I'm going to do is I'm going to look through and I'm going to mask out, I'll say, any east walls. Okay, so the idea with the east wall, the wall facing east, is if we have position I and position J, then we want to look at position in the same row, but the next column. And if we've got something in the next column, then we're going to mask out the east wall on our current position. But also we're going to mask out the east wall if we are on the eastmost side, if we're on the final column, because then we we can't look over, and it's not possible for the player to get around on the other side and look at us. So let's do that check first. We'll say if j farthest right, so col count -1. Okay, so this is a bit of a funny bitwise pattern that I've done here, or maybe it's not funny, I don't know. But the basic idea is the number 2 is all zeros except for, anyway, think of it like this. It's all zeros except for a 1 in the second, in the 2 position, right? Now, if I take the complement of that, then that becomes something like this. It becomes all 1s except for a 0 in the 2 position. And then if I take a bitwise AND with that, taking a bitwise AND with 1 will not change the current result, but taking a bitwise AND with 0 will, no matter what, zero out that position. So in other words, what this operation is doing is just clearing the bit in the 2 position. Let me just go ahead. So that's my edge case. And then we'll have this one. And I can probably, I'm feeling confident that Python is going to short circuit evaluate this, right? So the risk with putting these 2 together is if Python attempts to evaluate them both at the same time, then this bounds check can fail in some cases, but I'm going to see if this works. In fact, it does work. Now, as you can see here, we've now reduced our draw count by masking out the east walls. And we can probably hack it a little bit by going in. Does this work? Maybe not. Okay. I have had issues with getting that wall collision working smoothly, and sometimes it would let me look inside. But there we have it. We can see the number of draw calls has gone down. Now I'm going to do the same thing with the west walls. So with the west walls, it will be something very similar. We'll be looking to the left. So we'll be looking at, well, the thing to the left of us. So the column before, and then the bounds check on that will be, if we're in column 0, we can't look any further to the left. And then the corresponding bit with that will be the value of 1. Cool. Okay, let's give that a go. Okay, now as you can see, we have further reduced our draw count. We're down to 519 from 600, and performance is starting to improve. We're getting about 16 to 17 milliseconds per frame, which is more in line with 60 frames per second. But as you know, we can do a lot better. Yeah, this definitely should. But anyway, so south walls, edit, south walls, we're looking down, so we're looking at the row below us. So our bounds check is, if we're on the final row, and then our internal check is if we look at the row directly below us, and that position has a wall in it. And then the mask value there is 8. So we want to remove that. And then for the north walls, we'll be looking at the row above us. So the bounds check will be whether our row is 0, and the internal check will be directly above us with the final bit of 4. Cool. Okay. So again, to step through this, what we did is we loaded in all of the data, and then we looked through the array, because when 2 wall elements are next to each other, obviously the walls between them will not ever be visible. And so this will simply be masking out which walls are invisible, and then on the render system side, it takes in that info and it looks through, And for each wall, it also checks that mask to see whether that wall should be drawn or not. And this is the thing, we can do it once at creation. It doesn't interfere with our program too much. Okay, so in terms of what this actually does, currently you can see that we are down to 446 draw calls, and our frame time is, yeah, I would say about 14 milliseconds or so, 14 and a bit. So that's already a pretty good improvement. Now let's see if we can do better. Okay, so you'll note that as we're going through this in our render system, we are still sort of looking through the whole board and checking whether we've got something we should draw. Now this is a pretty reasonable approach, but it's also pretty wasteful because the map isn't going to change, and we should know upfront which things we can draw and which things we can't. So it would be better to upfront record a list of drawing commands and then look through them. Because when we've got a map, we're looking through it, some elements of the map will be no-op elements, right? We're not going to do anything. But loops are still expensive in Python. Whereas if we look through a list of draw commands, every single one of those draw commands will correspond with a valid operation. So that's reducing the amount of checking that we're doing. And it will also set things up pretty well for our work later on with dynamic optimizations. So what I'm going to do is I'm going to create a list of draw commands, both for the ceiling and floor. I'm going to batch those together, and for the walls. I'm going to create that and populate it. But in order to do that, I'm going to need to define a data type, because I want my performance to be as good as possible. I'm going to declare a NumPy data type for this, so I can have a NumPy array of draw commands. So it turns out that declaring data types in NumPy is pretty flexible and pretty good. We basically need to populate a dictionary, and the bare minimum that we need is just the names and data types. But for this, I'm also going to be explicitly specifying the offsets and item size, just to have as much control over this as possible. There we go. So this is all the information I would need to pre-record to specify an operation to draw a floor and a ceiling. I would need to know the row and column that I'm in and the material number for the floor and ceiling. The wall is going to be pretty similar. Just that we're going to need the material number for the wall as well as the mask number. Now for the mask number, uint8 is probably fine. For the material number, it needs to be a signed integer because we're going to have -1 indicating doors. But there we have it. I'm pretty happy with that. The next step will be to declare this stuff on the, what am I thinking? To declare this stuff in the component registry. Okay, so far so good. So the component registry, this is a bit arbitrary, but I'm going to leave it to the component registry to record those commands. For arbitrary reasons, we could do it the other way. We could make the world do it. But what I am going to do is I'm going to use the world to additionally fetch the command count for each of these, the draw count. And what I mean by that is when we go through and we update by loading in the data, I want to also keep track of basically how many elements were loaded, how many non-zero elements were loaded. So I'm going to go to the load array, and rather than simply return the array, I'm also going to return the number of non-trivial elements that were loaded into that array. There we go. Cool. Pretty easy. So then in terms of how we use that, I can go over to the stuff here. This is getting a little big, but we'll get the number of walls. And then here, I really, because I'm loading this twice, it really doesn't matter. I'll just, and because for every wall there's going to be a ceiling, the floor count and ceiling count will be the same. So the first time we ignore it, the second time we store it. Great. Then I'm going to tell my registry, well, I'm going to make a function that loads stuff in. But this is what we're going to do. We're going to go record wall commands. And then similarly down below, just like that. I think that's fine. Okay. And then we're going to need to specify these. There we go. Going to need to specify these functions over here. Now I'll just go right at the top, and I will my constants so that I have access to that draw type. So this is the cool thing about defining our own data types in NumPy, is let's say I need 10 wall draw commands. I can just issue like, hey, NumPy, zero out, give me a list of 10 wall draw calls, and it will populate all that info for me. Now the purpose of offset here is it will keep track of the index of the current draw command that I am writing. There we go. So as you can see, we sort of look through the whole map, and for every non-trivial wall element, we then go ahead and pre-record all the info that we're going to need to draw that thing. Cool. Yeah, let me go ahead and do the same thing for the ceiling or the floor, or both of them together. Okay, fingers crossed. I don't think I've missed anything there. Okay, so just double checking. It would not be the first time. Okay, now that's fine. So this has received the message to go ahead and record all of those commands. Now I'm going to go to my render system, and I'll alter this so that we can take in those commands. So instead of taking in all of this stuff, do we really not need all that stuff? Okay, right. So then I'll go down to the update, and then instead of looping through everything, take a look how simple this is. I'll just go for and we can get rid of all of this. Is that not nice? I don't know, I like that. Okay, but we are going to need to modify the drawing commands, or the drawing functions. For one thing, this draw wall is going to need to get modified, but secondly, draw floor and get ceiling are going to need to come together into one thing, but one step at a time. If I look here, I can see that these 4 elements are really just the things packed into the command. And that command under the hood is really like an array of all that info. So what I'll do is I'll unpack ij material, just like that. So I've unpacked it, and then I can start using that. So I've got my material for my row and column, that's my I and J, and then everything else, fingers crossed, should be fine. Now I'll do the same thing, and I'll get this all into draw. Yep, draw ceiling, draw wall together as one. So similarly, we'll unpack, we will bind the floor material, then we'll set the transform, and then this stuff will go ahead and draw it. And then what I'm going to do is I'm not going to reset the transform, because I don't need to apply a new transform. The transform is just in the horizontal, the IJ, the row column, and that's the same regardless of whether I'm drawing a floor or ceiling. So really all I need to do here, I think, is just fetch the appropriate ceiling number. And again, I'm really double checking myself, but I think we're fine. So let's go ahead and see what happens. Okay, totally fine. No field. Okay. That was, oh, I think I've got it. That's my bad. That is my bad. So what I did here is I think I accidentally did not change the data type. There we go. Very important. There we go. Okay, so there's 2 things to note here. Number one is that even though this has not reduced the number of draw calls, it has reduced the amount of empty space. We're not doing any dynamic, like looking through the whole map each time. We know exactly what the draw calls are up front. We're just flushing them out. There's no no-ops. And then secondly, having a tightly packed collection of draw calls is really useful for, well, it's a really good method that we can extend to the later optimizations. Okay, but I think we can probably leave this here for now. In the next video, we'll be having a look at dynamic optimizations. These are optimizations which are performed every frame, and they depend on some dynamic information like the camera's position, the camera's direction, and the world. But yeah, I hope you had fun, and I hope to see you again soon. Bye.